A really interesting part of your presentation was when you talked about some extractable studies that were commissioned by Watson-Marlow Fluid Technology Group. Tell us about them.
Okay, so we wanted to look at, bearing in mind of all this industry discussion that's been going on around extractables, we wanted to look at some of our product lines and determine, what are the extractables profiles from some of these components. And it was really to help us understand, from a kind of supplier point of view, what kind of data we were going to generate, but also to help our customers and support them in their risk assessment activities. So one of the things that we did was we looked at all the consensus protocols that were around, and we looked and tried to perform a study that made sense in terms of the types of solvents we're going to be looking at, the type of components we're going to be looking at, type of time frame, time points, temperatures. So all of these things were factored into the study that we then performed, or was performed for us. So one of the things we did was that we wanted to look at our silicon tubing. We have silicon tubing that's used in a range of different applications across the biopharm industry. We wanted to look at our BioPure polypropylene connectors, which again are used in a wide range of different industries, different parts of the process, of the biopharm process. And wanted to look even at things that are known to be have very limited drug contact, but we still felt it was important to understand about the nature of some of the components and the extractables from our BioPure gaskets as well. In the next few slides, I wanted to tell you a little bit about, or show you some of the data that we've obtained and how this data can be used in risk assessment strategies by end users. So this slide details the total number of extractables per component just by looking on the GCMS, so just looking at the semi-volatile analysis based on a 50% ethanol solution. What we found was that the highest number of extractables were from individual extractables, were from the silicon gaskets. The silicon tubing had the least number of individual extractables. But when you looked at the average concentration of those extractables, the tubing had the highest level average concentration, whereas the nylon clamps had the lowest concentration. So what we found there was that even though we had these gaskets, they had lots of little peaks, but they didn't actually amount to a very high level.
Now, the effect of solvents on extractables was interesting.
Yes.
The audience was interested in this. What were some of the most interesting findings in your mind?
I think the most interesting finding was, particularly when we're looking at some of the silicon tubing, that actually we didn't find very many extractables in aqueous media. So when we're looking at the aqueous and low pH solutions, we actually didn't find very many extractables that were attributable to the tubing. So there was no, whereas the 50% ethanol solution by far showed us a lot of the story of what the extractables profile was going to be, and that was really in every instance. When we looked at our range of components, the 50% ethanol solution by far and away had the most level of extractables in it. But it also gave us a picture to be able to understand if any of these compounds that end up as extractables, could they be of a safety concern? We were able to look at them, identify some of them, and determine that no, they weren't of a safety concern. This again is the analysis for looking for semi-volatile extractables by direct injection GCMS. We find that the most extracting solvent is the 50% ethanol solution. The least is for Wi-Fi and low pH. The highest single amount found was 0.7 micrograms per centimeter squared. Again, this is an evaluation of the semi-volatile extractables by GCMS. The highest single amount we found was 19.2 micrograms per centimeter squared. We found that for the polypropylene connectors, there are a lot of extractables that were soluble in water and high and low pHs. What we found from all of our studies is that no class 1 elements were found. These class 1 elements as detailed by ICHQ 3D, such as lead, cadmium, arsenic and mercury, are known human toxicants, and we did not detect any of those in our studies. However, we did detect a class 2B element when we looked at our silicon silicon tubing extract, but that's not surprising because we use platinum cured silicon material for the gaskets and for the tubing, so it's not surprising to find some small traces of platinum extracted. We also found silicon, not surprisingly, as an element, and barium.
During her presentation, Dr. Shadi Makolu also discussed how the sterilization method might affect the type and amount of extractables present. The research team looked at autoclave data for silicon gaskets, which were used as a representative component. They had been autoclaved for 60 minutes at 125 degrees Celsius.
When evaluating them over a range of different solvents, we again found the 50% ethanol solution was the most extracting, with the water and low pH being the least extracting. When we compare that data to silicon gaskets which had been irradiated at 50 kilogray plus or minus 10%, we find that for every single solvent type, the irradiated samples produced more individual extractables. However, when you interrogated the autoclave sample data, the total amount of extractables was greater in the autoclave data than it was in the irradiated samples data. When you irradiate samples, you're essentially you've got high energy bond cleaving processes that are going on, and this could lead to like small breakdown products of the polymers and the polymer additives, and this is what we're seeing in the baseline of these samples from the irradiated extracts.
Now, what did you find about how those components are made? What was the effect on the data?
Okay, so for example, we found that the way we manufactured our products could actually have an impact on extractables. One aspect that we've always done within Watson-Marlow Fluid Technology Group is we've always post-cured our tubing. So post-curing is the process by which after the tubing has been formed, we then take the tubing and then we do further heat treatments for 4 hours at 200 degrees Celsius. And the reason we're performing these processing, further heat processing, was to actually help us increase the degree of cross-linking in the polymer. What we didn't understand until we did the extractable study, that actually this was also helping to reduce the number of extractables that could potentially leach out of the tubing. So the other thing we found was that a lot of the compounds that came out of our polypropylene connectors were as a result from the polymer. So they're not compounds that are unknown, they're compounds that are known to be part of the polymers. So I think from a risk assessment point of view, that's something that can be of a comfort to customers, knowing that what we're finding is what we expect to find as a result of the materials of construction.
Are you planning any additional studies?
Yes, we are. We're planning lots more studies we want to be able to have these studies on all our fluid path components. So that'll be all our tubing, not just our silicon tubing, but our TPE tubing, our bioprene tubing, also a lot of our different connectors using different materials we want to be looking at. We also make hoses, so we want to be looking at generating data on our PTFE hoses, which we have as part of our Aflex line. That's another brand, another Watson-Marlow Fluid Technology Group brand. We're at the moment constantly trying to generate data, so to give our customers a good level of assurance that they're able to use this data to do risk assessments, so they can use that data to understand, well, this product, whatever the product is, will it have an impact on my drug product? And and be able to do those kind of risk assessment approaches. It's really critical now within pharmaceutical manufacturing.